No.
Great. I'll just continue then.
Cool. Yeah. Sorry for
Yeah,
the.
you're fine. So then three, the interconnects themselves. That you need to figure out how you're going to the interconnects and what this does to connectivity within the device. As well as like multi-qubit operations, not just 2 qubits, but perhaps you want to do multi-qubit measurements and so on. Specifically in the case of ion Q, we have trapped ion hardware. So normally you have all-to-all connectivity like on a single device. The moment you move to modular architecture, you're kind of losing this. So now you need to rethink what is this, like what kind of connectivity do you have? You have all-to-all connectivity within a module, but then what do you have between modules? The actual physical details of how the interconnects work, of course, is still a question. And then what is sort of the minimum connectivity that you need to still see advantages from this distributed approach versus just a large monolithic device? So in this case, we're kind of focusing on this idea of photonic interconnects. I'm going to avoid most of the hardware details and focus just on the things that you need to know to model this in simulations, because that's what we do in this work, obviously. Uh, and yeah, so photonic interconnects, the basic idea is we're trying to generate some bell pairs between multiple devices, and then we'll apply 2 qubit gates on physical qubits between these devices via teleportation. So pretty straightforward. The issue is you have to generate these bell pairs, which takes a while. You have to distill these bell pairs so that you actually have like a usable one, and you still have bad error rates despite that. And then you have to consume the bell pairs every time you want to apply a gate by teleportation. So for a single 2 qubit gate between two modules, this comes at the cost of an ancilla qubit on both modules. So 2 extra qubits already, decreased fidelities, and decreased run or increased runtime. So clearly we need to manage this. And it's kind of a question, an open question is it still possible to set up these interconnects in such a way that we keep an advantage over just using a single monolithic module? Right. So the actual main idea of this work is based on this Clifford noise reduction protocol, which IonQ published at this point, I guess, a few years ago. But we're assuming that there are an insufficient number of qubits to do this noise reduction protocol on a single module. And the question is, in that case, can we add more modules connected with these photonic interconnects in such a way that we can actually apply CliNR and get the advantages of using this protocol? We will find that we can actually improve the fidelity over the non-distributed case if we can implement CliNR. And this will improve the runtime as well, because you are actually parallelizing the circuit, which you'll see how that works later. It's important to remember that as well that we can kind of, if we're going to break this circuit into parts, we are already doing this via teleportation, then you already have some parallelization happening. But maybe this will be more clear when you look at the actual circuit. So first we have to explain what CliNR actually is. So CliNR just stands for Clifford noise reduction. The idea is that given any Clifford circuit C, which acts on n qubits, at the cost of a 3n plus 1 qubit overhead and a slight runtime overhead, we can reduce the error rate, like the logical error rate, by, I think it's around 3 times, but it is asymptotic, is the key here. So you can see the prototypical CliNR circuit here in this figure. There are basically 3 parts. There's this resource state preparation, where we have these 2 registers of n qubits each that we assume are in bell pairs. We apply the Clifford circuit to one of these registers, just the Clifford circuit like as you get it. And we kind of hope that that circuit is correct, or that is applied correctly without errors. Then we get to resource state verification, where we measure some randomly selected stabilizers on these 2 registers. And these are all controlled by a single ancilla. And then based on the measurement taken on this ancilla, we can see if any errors have occurred. And this is just a simple error detection circuit. And of course, it's not so robust because you're choosing stabilizers randomly and you're actually not choosing that many stabilizers. But in practice, in expectation, you actually will catch the vast majority of the times that C is not prepared correctly. And of course, if you detect an error, you just restart and you do this again. And the key insight here is that RSP and RSV are totally disconnected from your actual register that you want to apply the Clifford circuit to and the rest of the circuit. So this can all be done and prepared offline. However, this is already 2n qubits, already with well pairs, or 2n plus 1 qubits actually when you take into account the epsilon. And if you're doing restarts, then you're applying the whole Clifford circuit multiple times. Finally, once you've verified that you actually have the circuit correctly implemented, or the Clifford circuit correctly implemented, we can inject the state back onto our input register, and we do this just by teleportation. So entangle with the second register, measure, and then we apply some corrections Q. And the details of Q aren't so important, but you can determine it efficiently because this is a Clifford circuit. And if anyone's particularly interested, I can show you what it is later in a backup slide. You may recognize this as essentially the coherent parity check protocol, but adding teleportation into it. It's really just like a pretty simple adaptation of that. Also, I mentioned it briefly, but because C is Clifford and all of this is Clifford, Q can be calculated efficiently. That's the only reason this works. If some part of this are non-Clifford, then you wouldn't actually know what Q is, and then you'd have issues. In practice, the choice of stabilizers does not actually matter. You can be clever, saying, okay, we expect these errors to occur more often than others, like depending on your noise model, maybe it's extremely biased. And then you can choose stabilizers in a way that you detect errors more often. But even if you just choose stabilizers uniformly at random, you're actually fine even with only like 3 or 4 stabilizers chosen. And the proof of that is pretty interesting, or not so interesting, but it's pretty nice. Then the final minor detail, which you might have noticed if you're looking carefully at the circuit, our final state is not going to be on the same registers that it started on. It's going to end up on these final n registers, which that does matter later because it means we might have to care about swaps. If this is a single device, obviously we don't care because we have all-to-all connectivity. But if maybe those 2 registers are on different devices, now this matters a lot. Right. So there are a few things we can do with CliNR to extend it. The first insight is that sometimes C gets quite large, like the Clifford circuit itself. In that case, the probability that you need to do a restart just becomes absurdly high, and you're never actually going to apply C successfully. So to alleviate this, you just break the Clifford circuit into parts and then do CliNR on these parts. We would call this a CliNR chain. This figure down below is basically a much more complicated version of that, where we also consider the fact that the CliNR protocol itself is all Clifford. So you can actually do the CliNR protocol where C is the CliNR protocol itself. And by repeating CliNR kind of recursively, you get these CliNR trees. So you can further reduce the noise at the cost of more qubits. So you can combine the 2 ideas, and you basically are breaking your Clifford circuit C into like 2 parts here, doing CliNR on each part in sequence, then doing CliNR on that entire thing to reduce the noise rate further, and then doing it again for another part of C, and so on. So you can kind of take this really far if you want to. It has some advantages, it has some disadvantages, as you'd expect, but that's another paper that Aaron and Nicola published a couple months before the one that we're talking about now. We're not going to deal with CliNR trees in this work, but we are going to deal with CliNR chains. And again, that's just a depth 1 CliNR tree is the easiest way to think about that. Right. So now we can finally talk about distributing CliNR across multiple QPUs. I mentioned that RSP and RSV are offline. The clear intuitive thing to do then is split the circuit such that the offline component happens on 1 QPU and the actual teleportation part happens on another. So here if we consider it's just 2 QPUs, Q0 and Q1, and we do our state preparation verification on Q1, then once this is ready, we do our injection via intermodule gates on Q0. Note here that we still need n intermodule CNOTs. This is probably minimal for this protocol. I mean, it pretty much like is. You'd have to prove that in some way if you're the one to, but we don't really care about proving that necessarily. But also we mentioned that photonic interconnects require ancilla. So what are the costs here? Well, for these intermodule qubit or 2 qubit gates, we now need this Q0 module, not just to have in register in qubits for this register, but another in qubits for all of these intermodule gates. So you already have 2 in here. And then Q1 now, instead of having 2n plus 1 qubits, it actually has 3n plus 1 qubits because you also need epsilon Q1 for these intermodule gates. And so now you have exactly the number of qubits that you already needed to do CliNR. So in this case, why wouldn't you just do CliNR on Q1 on its own? Right. So clearly this is sort of a toy example, just the basic idea to show that you can distribute it across 2 modules, but in practice, this would make no sense. However, we are still retaining this offline nature of RSP and RSP. So what if we have more than 2 QPUs? Well, now we can get a bit clever here. I mentioned CliNR chains before. Let's take some large Clifford circuit and break it into multiple sections, like more than just 2. So in this case, C is being split into 3 separate components. And we're going to do basically a CliNR chain, but do the state preparation verification in parallel for each part of this chain. If you had a single device, like in this case, you have to do this serially, right? Now we have the advantage of doing these in parallel because we have multiple devices. And so you do your state preparation verification and you do your injection, but you have to do injection between each QPU. The nice thing about this is that your injection step becomes essentially this sequence of injections. And actually you can be a bit clever with this extra space between each injection. Like this is just idle time that you can use for maybe doing a slightly larger Clifford circuit or doing some other work. And then you just do your final teleportation back to the original register to have the, if you want to have the final state in the register you expect it to be. Note here, because we're doing the injection in this chain, we're actually avoiding doing this final amount or this final swap step on each of the intermediate parts. That's really nice because if you had to do swaps, that would be more intermodule gates. And it's worth remembering that even this is intermodule 1. It's actually 3 intermodule gates because of the swaps. We're also retaining the parallelization that we get from doing this via teleportation. So you might think about the costs themselves, or the qubit costs. We again need 3n plus 1 qubits for each of these modules, and actually you need 4n plus 1 qubits for each of these modules. But the key here is that if you were to do this on a single device, you wouldn't have all of these qubits. You would just have 3n plus 1 qubits, and all of this is now serial instead of parallel. So basically, we're getting runtime improvements as well. Right, so we simulated all of this. We did this all in STEM. The noise model that we used is basically a modified version of the depolarizing noise model. It's not exactly the ion chain model, if you're familiar with that, because that would also require us to consider all of our 2 qubit gates to be serial instead of parallel, which we don't do that. But basically, for whatever the error rate is, we consider 2 qubit gates to have that error rate, 1 qubit gates to be a tenth that error rate, measurements as well. Idle time is just 1/100th the error rate. And then our intermodule gates, we consider to have 3 times the error rate of a normal 2 qubit gate. This is admittedly pretty optimistic, but we're trying to just say, like, in a kind of best case scenario, does this work? Does this make any sense at all to try? There's also this quantity tau sub e, which I will use a few times later. This is the entanglement generation time. So it's the number of time steps it takes to generate a single bell pair successfully. We're going to assume that the moment the circuit starts, the device or all devices are trying to generate bell pairs immediately. And exactly which other devices they're generating these bell pairs with, I'll get into later. But yeah, this idea is that every tau sub e time steps, you're going to get a bell pair generated. Finally, these Clifford circuits C that I mentioned before, we're going to assume that they're all just uniformly chosen or uniformly random Clifford circuits with exactly n squared gates. This is because if you had any larger, well, you can always reduce such a circuit down to exactly n squared gates, or at most n squared gates. And then stabilizers, again, we're choosing them uniformly at random. You can get slight improvements by being clever with your choices, but it's not really necessary. Right. So here are some easy to read results, I think. The direct line here is just the Clifford circuit itself with no cleaner at all. Monolithic is basically on a single device where you're applying cleaner, but you're doing it as a cleaner chain, so a 3-node cleaner chain. And this is all serial instead of in parallel. And then distributed is the case we talked about before. Actually, it's exactly this figure. Or I think it's actually just Q0, 1, and 2 instead of 3. So you can see that we get slight improvements to fidelity, or this is kind of the expected improvements to fidelity over the over just applying the Clifford circuit directly when using cleaner. And we retain those improvements when we use distributed cleaner. So the increased noise rate from the intermodule gates has very little effect on the overall error rate of the circuit, which is exactly what we wanted. But then the interesting part is that our runtime actually improves as well. So normally this improvement in fidelity comes at a cost of runtime here. And that's what you can see with the difference between the yellow line and the blue line. But in the distributed case, we actually get improvements in the runtime over even the normal Clifford circuit just being applied directly because we're splitting the circuit into parts and parallelizing. So we get both the logical error rate improvements and the runtime improvements simultaneously. So it's exactly what we want to see. However, in the title, you'll notice that we have the slow cost out. This is assuming the entanglement generation time is set to 1, so we're totally ignoring the slow interconnects. We're just considering them with normal interconnects. Here's what happens when we actually consider slow interconnects. So these are the same experiments as before, just the x-axis is now this tau sub e quantity. And we chose some nice values kind of in the middle of the curve on these graphs and just plotted those with increasing entanglement generation time. And you can see pretty much exactly what you'd expect. As the entanglement generation time increases, at a certain point, this time of just idling and waiting for more bell pairs to be generated so that you can do the next set of intermodule gates overwhelms the rest of the circuit, and that takes up all of your runtime and causes a lot of error through idle errors. However, it doesn't happen immediately. I mean, it's not like you can handle hundreds of time steps of entanglement generation time, but it is around like 5 or 6 is where you start to actually see issues. It's not until 6 for the error rate improvement and 12 for the runtime improvement that you actually lose your advantage. So it's not great, but it is usable. Like you can, with slightly slow interconnects and slightly noisy interconnects, still get these advantages, which is exactly what we want. There's some other minor implementation details here. I mentioned that you still have fairly large QPUs. Actually, you'd want the QPUs not to have 3n plus 1 qubits, but 4n plus 1 qubits, so that they can connect between the previous QPU and the next QPU in the chain. And you would set this up kind of as a ring. So Q1 would generate bell pairs with Q0 and with Q2 simultaneously. And then you would consume these for these RSI steps, but then you never have to communicate, for example, between Q1 and Q3. And this limits the size here, or the size of your QPUs, and also makes entanglement generation much more manageable. Also, 4n plus 1 is still not enough to parallelize the previous circuit in any meaningful way that you'd get anywhere near the runtime advantages that you do here. So again, we refer to this as a ring topology. And it does take a lot of photonic interconnects, which is kind of an open question how you would get all those working. But this is a setup that does work. The idea is that you're generating I bell pairs basically every tau sub e time steps because you're generating all these bell pairs in parallel with this ring topology. And I believe that is the last slide. I have a couple backup slides if anyone has questions, but otherwise I'd just be happy to answer anything.
Thanks, Evan. Any question from the audience?
Maybe this is just ask a question. Oh, first of all, thanks, Evan. This is really good to hear. Like putting this in broader context, how do you, I'm less familiar with whatever other state-of-the-art strategies or techniques there are in distributed, quantum here. Are there like competing methods you would consider, or like how does this fit into the landscape? I guess is a simple way to ask my question.
Right, right. So within trapped ion devices, I'm not aware of any protocols besides using photonic interconnects. And I'm not so familiar with what people want to use, for example, in the superconducting case. For some reason, I want to say it's actually, again, just photonic interconnects. But again, I'm really not familiar with that. Sort of competing protocols, though. And the idea is that this is like not error correction, right? This is like it's somewhere between error mitigation and error correction. And so one way of thinking of this is like an alternative to full distributed error correction in the near term.
Got it.
Not sure how well that answers your question, but
I think it helps. Yeah.
Okay.
And then maybe I think then the answer about to like, how far away would you be from like having two trapped ion devices that like somebody could actually test this? Do you have any idea? Like that pretty far away?
Right, right. So I can't speak to the photonic interconnects hardware. I know that that is something that's being worked on by many people, and that that's like clearly the goal. And my understanding is that this is a fairly reasonable example of a circuit that you could run to show that you get actual improvements, right? In terms, like, yeah, I guess that's all I can really say is that I can't give you estimates on how far away. I can say that it is something that's being worked towards.
I do have a quick. Oh, go ahead, man.
Yeah, I do have a question. From your point of view, what is going to be the biggest bottleneck for distributed quantum computing? Is it the hardware efficiency that you need to do it, or will it be a problem coming from the algorithms requiring way too many interconnect for things to be practical?
That's an interesting question. My intuition is that the hardware will be more limiting than the algorithms, but this is because I'm an algorithms guy. Like my background is in compilation and algorithms. So when I think about how would we try and distribute, for example, error correction protocols and things, it seems hard, but it doesn't seem impossible. Like I see ways that you could try and go about it. When I think about the error rates that we're getting on these interconnects, for example, or getting single devices with good enough error rates and enough qubits for this to be reasonable, that's more of a black box in my mind. So intuitively, I just think that's probably going to be the more limiting factor. But there's definitely a lot of work that still needs to be done on the compilation side as well, especially for error correction. I think there's a question in the chat as well. If somebody
Yeah,
can
let me read it out. Have you found a time frame below which this isn't necessary and or above which this is always necessary?
By time frame, do you mean tau sub b, like the entanglement generation time? I guess I'm going to just assume
Assuming
gates.
Peterson gates.
Do you mean like number of gates? If you mean like
I guess the depth.
yeah, I guess that's like the only thing I can think of. It's like if you mean like the number of gates or circuit size, basically, like above which this is helpful and below which there's no reason to do it. We did think about doing that, and the short answer is that you get really nice results if you make your circuit sizes like 10 n squared. But that's obviously like really not realistic, and you would never have a Clifford circuit with 10 n squared gates. Like you just wouldn't ever. And there's a reason that we keep the circuit size at n squared, because it makes the results actually visible. You can reduce it slightly below n squared and still see this kind of nice gap in the lines that we like, and that really shows where you get advantages. But you can't go so far below it. So it's kind of a narrow window of circuit size. But you can imagine if you have any large Clifford circuit ever, or at least large enough that you want to compile down to n squared gates, then this becomes reasonable.
I hope this answers his question, Peter. Yes.
Great. I'm glad we were able to correctly interpret it.
I did have a question about these slides, the simulation results.
Yeah.
How much does this depend on that assumption that the error rate for the interconnect is like 3 times the error rates of the 2 qubit gates? Like, would these lines still overlap on the first graph? Okay.
Yeah, I'm glad somebody noticed that. So I'll say we simulated this with a few different error rates there, like for the inner module gates specifically. It depends heavily on that. I think you can get away with like 5n squared even. I want to say once you assume it's like 10, or not 5n squared, sorry, 5p. Yeah. But I think if you go up to like 10p here, then you really don't see that gap anymore. Unless, of course, you increase circuit size. Basically, it's the larger the circuit and the lower this error rate, the better the results look, right?
And what's a realistic intermodule gates on like the current?
Yeah, I can't speak too much to that, I guess, because I'm not the harder guy. My understanding is that they're fairly far away from this, but I think it also depends on how much distillation you're willing to do, like how long you're willing to take to actually generate these bell pairs. But I would say this is also like, this is a similar idea to like asking about error rates in current devices. Like you'll get the answer of what's released right now, and then a few months from now, there will be something released that has like way better fidelities. And you're like, oh, I wish I had known that existed.
Yeah, I was wondering more like proportionally to the 2 qubit gates. So I guess 10p would still do.
Yeah, I think
yeah.
10p was like, I remember when we were doing this work, we were really hoping that 10p would work. And we were quite disappointed when it didn't. But we're still, I think, fairly optimistic about the fact that even at 3p, this works.
Yeah.
Because I guess the other way of thinking about this is 3p is kind of the minimum, because when you apply these gates, you're doing them by teleportation as well. And so it's not just a single 2 qubit gate, right? It's actually 3 2 qubit gates. Yeah.
Any other question from the audience? If not, let's thank Evan again. And yeah, it was good to see some distributed quantum computing. We don't have it often. So thanks a lot for your talk.
Thanks, Evan. Really cool.
Thank you for having me, and thank you for the questions. I'm glad everybody kind of asked the fun questions that I was hoping to get.
And yeah, well, if anyone has follow-up question, they can continue the discussion on Discord on the Quantum Wednesday channel.
Yeah, and I think it's easy to find me on the Unitary Foundation Discord as well. So feel free to DM me if you have any specific questions. And there are archive links as well. They should be in the recording too. So feel free to go look at the paper itself. There's some more theoretical results there.
Yeah, I will post the link on the channel again.
Great.
Thanks again.
Thank you.
Bye, everyone.
Thank you,
Bye.
Evan.